Alright, in this video we'll begin section 12.5, which is tangents and normals to curves. So first let C be a smooth curve given by the vector function R of t. The unit tangent vector to C is the vector capital T of t equals the vector R prime of t divided by the magnitude of R prime of t. So I've briefly in a previous lecture spoken about the tangent vector. This is that same vector. You just take your position vector, take its derivative, but now this is that vector divided by its magnitude. So this is the unit tangent vector. So it's the same vector, points in the same direction as that vector. It's just now scaled to have length 1. So just the same comment I mentioned about the tangent vector initially, or I talked about it in terms of their derivative, but then I explained that it was tangent to the curve. So this vector is tangent to the curve C and determines the orientation and determines the orientation of C that is capital T of t points in the direction of travel. So if you look back in your notes, you'll see a picture of this that I drew a couple of lectures ago. It just wasn't the unit tangent vector, it was just a tangent vector. Next, the unit normal vector to the curve C is capital N of t. So it's a vector capital N of t, which equals capital T prime of t. So you take the derivative of the unit tangent vector. So you take the derivative of this and you divide it by its magnitude. So the magnitude of the vector capital T prime of t. This vector is perpendicular to the vector capital T of t, or the unit tangent vector. So now that we have that these two vectors are perpendicular to one another, we can resolve any vector in the plane that they make into vectors parallel, a sum of vectors parallel to these two vectors. So given that the unit tangent vector and the unit normal vector are perpendicular, we can resolve any vector in the plane determined by the vector capital T of t and the vector capital N of t into a sum of vectors, parallel to the vector capital T of t and the vector capital N of t. Given a vector function R of t, both v of t is velocity and a of t is acceleration, are in the plane determined by the unit tangent vector and the unit normal vector. So that that means that we can resolve both v of t and a of t into a sum of vectors parallel to t of t and n of t. So that's the next thing we're going to do. Talk about the key thing we're going to talk about is what's called when we resolve a of t into a sum of vectors parallel to t of t and n. But we're also going to do with v of t as well, though. So when we do that, we get v of t equals some scalar. We're just going to call that scalar v sub t, where t is the unit tangent vector, and then times the vector, the unit tangent vector, plus the coefficient of the unit normal vector. We're going to call it v sub n. So these lowercase v's are scalars. Their name just has the name of that scalar. We're calling it v sub n because it is the coefficient of the unit normal vector n. So this is just a notational thing where the scalar v sub t is just equal to the magnitude of your vector v, and then v sub n, that scalar, is just going to always be 0. So basically, this says if you want to write your velocity vector as a sum of vectors, each of which is parallel to the unit tangent vector and the unit normal vector, then this coefficient is just the length of v, and this coefficient is 0. And that makes sense because this is the unit tangent vector, and v of t is r prime of t. It's the tangent vector. So to get this vector, which say, for instance, has length 10, we multiply it by, we take the unit vector that points in the same direction and just multiply it by 10. So there's nothing fancy going on right there. So that's why I said we're not going to be as focused on this one. This vector right here and that vector right there point in the exact same direction. This is just the unit vector of that vector. So we multiply this vector by the length of that vector, and we get that those are the exact same thing. Now a of t is a bit more involved, and the scalar coefficient for the unit tangent vector, we're going to call that a sub t, plus the coefficient for the unit normal vector, we'll call that a sub n. And now how do we compute these two things? So where a sub t is the derivative with respect to t of the magnitude of the velocity, or you can compute it another way. You can do the velocity dotted with the acceleration divided by the magnitude of velocity. So one thing to make note of, I'm not putting t's in here right now. It's just a shorthand notation, but this is a function of t. These scalars that you have may or may not be functions of t as well. So this is a function of t, capital T, that capital N is a function of t. Notice if I take some vector r of t, right, and then I take its velocity, then that's still a function of t. And then I take the magnitude of that velocity, it's still a function of t. It's a function of t until I plug in some number. It will remain a function of lowercase t. So all of these things that you see on here are functions of t, although I don't have them written that way. And I just aligned it with the textbook's notation, where they use the shorthand notation in this for this portion of the section, and leave the t's off. But please don't think that, okay, this is a magnitude of velocity, this is some number. It's going to be a function. It will be a scalar function until you plug in a value, then that becomes a number. So I point that out mainly because all of a sudden I start saying the derivative with respect to t, and you may think, well, that's just some number, some scalar value, so this is going to be 0. This will be a function of t, because again, r is a function of t, so that means its derivative, r prime of t, or v, is a function of t. And now you're just taking the magnitude of that vector, which is a function of t, and you're still going to get a function of t here. All right, so next is what is a sub n? So in a sub n equals, and there are two ways you can compute this, the square root of the length of acceleration squared minus, now you'll have to already have a sub t if you choose this route, minus a sub t squared. So this right here is just acceleration. So r double prime of t. This, on the other hand, is that value right there. Or you could also do the magnitude of v cross a. So you cross velocity with acceleration and then divide by the magnitude of velocity. And that will give you these coefficients. So oftentimes you'll be asked to find the tangential and normal components of acceleration. And that's so a sub t and a sub n are called the tangential and normal components of of acceleration respectively. So let's underline those: tangential and normal. So oftentimes you'll be asked to find a sub t and a sub n. All right, so I'm going to stop this video here and we'll continue in the next video, wrapping up the notes for this section, and then we'll work on some examples.